In Chapter 7, we start dealing with probability, which has a lot of similarities between what we just got done talking about, doing counts and permutations and things of that nature, and what we're doing with probability. It's just basically adding an extra step to the mix and figuring out, like, what are, like, the, of course, the probability of something happening. So we start off with some very similar sounding things we talked about before. An experiment is basically an activity where there's certain results. And these results can be a sample point, which is one outcome of the experiment, a sample space, which is basically all sample points are all possible outcomes, and an event is a subset of that circumstance. So um, and these definitions are very familiar with you because we talked about them a lot in the previous units or the previous chapter. So a union of two events, an intersection of two events, and of course a complement we've talked about in the previous chapter. So this first question, this first example that you're going to be given is more or less a problem that you dealt with from the first one, except from chapter 7 or chapter 6. Except, in chapter 6 you were asked to count them. Here you're just asked to list, what these various events are. So you're given that the sample space A, B, C, D, E, and F are all the outcomes of an event. E, F, and G, as they're described there, are particular events that are subsets of that sample space. You're asked to find these four things. So take a moment, figure out what these are, and we'll go over it momentarily. Okay, so um, for A, we're looking for all elements that are contained both in E and in F. And looking at them, I can see the only element that's in both of them is A. So that's what this subset would be. It's just, a subset with the one element A. For the union of F and G, well, F and G are, I can see that one, and I mean, they both contain half of what S is, but they don't have anything in common. Well, that's okay for a union. If it was an intersection, I would say that, there would be the empty set. But for this, it's just going to basically be the same thing S was because, F has three of the elements from S, G has the other three elements, so together they're going to make up S in total. For the intersection of E and the complement of G, well, first I got to figure out what the complement of G is. And because we kind of talked about it before, I mean, I could have also called the complement of G F. Because, that's the way that their relationship was. They each consisted of half of what S was, and they didn't contain anything in common. So they each had, three elements, which were, three of the six elements in sample space S. So it's no surprise then that when I take this intersection, it's the same thing as I had before, where I have basically that's just the set of A. And of course, the union of the complement of E, and the complement of F. The complement of E, of course, is everything except A and B. And the complement of F, of course, is everything except A, D, and F, which I could also just say is G again. So I could have rewritten this a couple of different ways, but I can see now what they have in common, what they don't have. It doesn't, I mean, what they have in common isn't as much big of a deal because it's a union. I mean, as long as it's in one of them, I count it as part of the union. So basically, this is going to be B, C, D, E, and F, or basically anything except A. One of the things you're going to see throughout we deal with probability is talking about mutually exclusive events because certain formulas are used to find probabilities only under the circumstance that they are mutually exclusive, and there's other things you have to use if they're not. So, of course, the mutually exclusive events are two events, both of which cannot occur at the same time. So they basically have no intersection. So you're asked here, going back to the stuff from example 1, are these events mutually exclusive? Are E and F mutually exclusive? And are the events E and F and E and the complement of F mutually exclusive? So take a moment, figure out what these answers would be, and then we'll go over it. Okay, so are E and F mutually exclusive? Well, from the previous example, we had figured out what the intersection of E and F was, and that was A. And A is not, I mean, that's something. It's not an empty set. So there is an intersection between them, and because of that, they are not mutually exclusive. A lot of students get confused with mutually exclusive because you're running a test to see if they have an intersection, and if the answer is no, then yes, they are mutually exclusive, or vice versa. If like, okay, well, is there an intersection? Well, yes. So no, they're not mutually exclusive. Are the events E and F and E and complement F mutually exclusive? So when I did E and F, or E and F, of course that's the set A. When I look at F, the complement of F, which is just again G, so if I look at E and G, the only thing they have in common are B. And so these are the two events, and I want to see if these two events are mutually exclusive. Well, one just has A in it, one just has B in it, so obviously they do not contain any of the same elements, so there is no intersection. That means the events are mutually exclusive. For example 3, you're told to let S equal the numbers 1, 2, and 3. They're associated with events that are occurring in an experiment. List all possible events of this experiment, which means basically you want to list all possible subsets of this. So they could contain just one element, multiple elements. So you want to list all of them. You want to tell me how many subsets contain the number 3, and how many subsets of S contain either the number 2 or the number 3. So take a moment, answer these 3 questions, and then we will go over it. Okay, so again, all events for this experiment are any and all subsets of the sample space. So the empty set is always considered to be a subset. I can have a set of nothing from S, so it is possible. The set of 1, the set of 2, the set of 3, those individuals would be subsets. I have the set of 1 and 2, the set of 2 and 3, the set of 1 and 3, those would be subsets that contain 2 elements. And of course, I only have one possibility for a subset that contains all 3, and that's basically S itself. So any sample space could be a subset of itself. So now when I go and answer the questions for B, having these listed does make it easier for me to answer the question, because it's asked how many subsets of S contain the number 3. Well, I can see there I had 8 subsets, 4 of them contain the number 3. So I could say 4 of them, in this case 4 of them, but eventually when I start talking about probabilities, I would say, okay, well, half of them do. 4 out of 8, so 50% of them would contain the number 3. How many subsets of S contain either the number 2 or the number 3? Well, again, I look at that, and we always assume that if we're given an either or, when we talk about probabilities and such, that it's always considered to be inclusive, which means you include both of them. If there's both is part of that. So this doesn't say either 2 or 3, but not both. It's saying, okay, either 2 or 3, and both would be considered part of that as well. And as you can see, 6 of them have either the number 2 or the number 3 contained in it. Example 4. As part of a quality control procedure, an inspector at Bristol Farms randomly selects 10 eggs from each consignment of eggs he receives and records the number of broken eggs. What is an appropriate sample space for this experiment? Describe the event E, that at most 3 eggs are broken, and describe the event F, that at least 5 eggs are broken. So basically, um, what you want to use for these before I turn you loose onto them is when you're looking for an appropriate sample space, you're looking for, well, okay, if we're going to let the numbers in this sample space, it should stand for the number of eggs that are broken. So you have to think, well, how many eggs could be broken? So you want to think of that as you're writing out, okay, well, what list of numbers would describe the number of eggs that could possibly be broken? And then E and F being subsets of that, how would you write those out to be, um, you know, based on their description? How would you what elements or what elements from S would fall into that? So take a moment, see if you can answer the question, and then we'll go back to it. Okay, so what is an appropriate sample space for this experiment? So basically, since I have 10 eggs, and what we're looking at are the number of eggs that are broken, then basically my sample space can range from 0 to 10. And so it's going to be all integers from 0 to 10. Because it makes sense. I mean, I could have 0 eggs broken, 1 egg, 2 eggs, 3 eggs, so forth and so on, up to 10 eggs broken. I can't have less than 0 eggs broken because I'd have to have negative eggs, which I don't makes any sense. And I certainly can't have 11 broken eggs out of 10, okay, or any number bigger than 10 because it wouldn't make any sense. So this would be the sample space. Now, as far as E goes, describe the event E that at most 3 eggs are broken. Well, at most means, the highest I get are 5. So any number up to and including 5, or no, sorry, I was looking at B for its description and then looking at the number in C. At most 3. So any number leading up to 3 or less would be falling into the set. So E would be described by the subset 0, 1, 2, and 3. And at least 5 eggs for F, that would mean 5 or more. So F would be described as 5, 6, 7, 8, 9, and 10. We're going to make use of these kind of ideas about thinking about the possible events when we start getting into more probability things and coming up with what we call a probability distribution, which in many cases does make finding probabilities, especially for more complicated events, a lot easier. But now we're going to get into what probability really is, because right now we just kind of repeated a lot of things we did when we were doing counting, thinking about like, well, how many different possible outcomes are there? How many, what are these subsets going to be? Well, now we're going to use these to figure out the probability of something occurring. So the probability of an event in a uniform sample space. Now, a uniform sample space basically means that everything has an equal chance of occurring. That's not always going to be the case. I mean, like if I'm flipping a coin heads or tails, each one has an equal chance of occurring. I mean, we're assuming it's not loaded in some way or, it's double-headed, anything like that. So each event has an equal chance of occurring. That's not always the case. So, um, you know, so you have to kind of keep in mind about that. And also, we're going to be starting to looking at things that are mutually exclusive. So if I have two different things going on, the outcome of one is not going to necessarily affect the outcome of another. So for an example here, a nickel and a dime are tossed, and the result of heads or tails is recorded for each coin. What are the simple events associated with this experiment? So take a moment, think about the fact, and as you think about this, keep in mind that we want the sample space to be all members described by the nickel result, then the dime result. That's how we'll define it. So what are the possible outcomes for this event? So the simple events, well, I could have the nickel be heads and the dime be heads. I could have the nickel be heads and the dime be tails. I could have the nickel be tails and the dime be heads. So this one's behaving more like a permutation because of the fact that it does matter. Saying one's heads and one's tails is different than me saying the nickel is heads and the dime is tails. So make sure you keep the difference in mind. And the last one, tails then tails for both the nickel and the dime. These are the simple events. And basically, each one would have an equal chance of occurring. So I could say each one of these would have a 1/4 chance of occurring because it's a uniform sample space. Finding the probability of an event. So what we want to do first when we find a probability is we determine a sample space with the experiment. Some of that's going to be using some of those counting techniques we learned in the previous chapter. So you have to keep some of those in mind as you go through this. We want to assign probabilities to the simple events of S. Do you have to do it for every possible event? Not really. It depends on how big if you have a relatively small probability distribution, you only have a couple, like maybe 2 or 3 possible events, and you might as well. But sometimes you can have several different, or many different outcomes or events that could occur within an experiment, and coming up with, the probabilities of all of them could take quite a bit of time. I mean, there's shortcuts we're going to learn about, but we want to try to make our lives a little easier. So sometimes it's just best to consider the events that are, that we're looking at that given moment. And basically, if you come up with the fact that if E is the empty set, then the probability of that occurring is 0. So they're going to talk about an empirical probability distribution. And basically, it's just a table. Now, sometimes they'll give you a table of data, and all you have to really do is just kind of like continue it and come up with a few other things with it. So you don't have to like rebuild an entire table. But basically, you have an event and you have a probability of that event. Those probabilities should total 1. So if you're coming up with an entire probability distribution, the sum of all the probabilities should equal 1 or 100%. Sometimes they describe probabilities using percentages, but usually we leave it in decimal form. So it really depends on how the question's asked, and oftentimes they'll say what percentage, when they want a percent instead of what is the probability. But all the probabilities should total 1. It's important to note that because sometimes you might have to take under consideration, okay, am I missing an event here that I need to consider when making this calculation? And sometimes logic will dictate whether or not, there is a missing one, and, if it's the only possibility that's left, and you say, well, I can assume the probability of that occurring is going to be this based on the fact that they all have to total 1. But let's see how we can use an empirical probability distribution to answer questions, especially as they get a little bit more complicated. So in example 2 here, you have a survey of 1,000 social media account users. The following questions was asked. How many social media accounts do you have? The results of the survey are summarized below. So basically you're being told that 650 of the respondents out of the 1,000 had 1 to 2 social media accounts, 200 of them had 3 to 4, and 150 had 5 or more. They want you to determine the empirical probability distribution associated with the data, and you can do the entire distribution because of the fact you only really have 3 subsets. You only have 3 events because they're only going to fall into the category of 1 or 2, 3 to 4, or 5 or more. And that does total 1,000. So basically, if it didn't total 1,000, you could probably assume that the remainder would be those that don't have any. So, but since the 650, the 200, and the 150 do total 1,000, then all 1,000 people in this in this media account users. And as I said, since they are saying you have social media account users, you're not going to have any that have none because they wouldn't fit into this category. Um, so so sometimes students will try to like put that in there. Say, well, you can have none. Well, if they're only looking at people that have social media accounts, you're not going to have anyone that has none. If they said we took 1,000 college students and asked the same question, then you might have a probability of having none. Maybe, who knows? So take a moment and see if you can come up with and pick out which table would describe the probability distribution for this situation, and then use that idea to find the probability that a participant in the survey selected at random answered that he or she had 3 or 4 accounts. So take a moment and we'll go over it momentarily. All right, so an empirical probability distribution basically is just me listing the events and the probability for each one of them. So my events are that x is between 1 and 2, x is between 3 and 4, and x is 5 or more. And based off of the numbers I had, the probability of x being between 1 and 2 is 650 out of 1,000. For x being between 3 and 4 is 200 out of 1,000. And of course, for being 5 or more is 150 out of 1,000. And these can be turned into decimals. And oftentimes you're going to see them written as decimals. And you should always guarantee that they do total 1. Because if they don't total 1, that can cause a lot of difficulty along the way. Now in part B, and you really didn't have to come up with this entire table to answer. Matter of fact, most of the table was already there. If you knew you had 200 people and 1,000 social media account users, and you know 200 out of 1,000 had between 3 or 4. So it's still going to be 0.2, or if I wanted to say about 20%. So if I pick a person from this study at random, it's a 20% chance that they have between 3 or 4 social media accounts. So let's look at example 3 here. So you have this table. You have payment methods versus the percentage of transactions. Now they're telling you these are percentages. So it's a good idea still to make sure they do total 100. And they do. Because then you have to say, okay, well, if I don't have a legitimate probability distribution, then, I wouldn't be able to answer these questions accurately. So it's always a good idea to check to make sure that you do have a table that represents a good probability distribution. And I could even write the probabilities like this. So basically in this one here, you're asked if a transaction tracked in the survey is selected at random, what is the probability that the transaction was paid for in part A, a credit card or a debit ATM card, and in part B, with cash or some other method other than a check, a credit card, or a debit card. So take a couple moments, figure out what these probabilities would be, and then we will go over it. All right, so we're looking for the first one, the probability that the transaction picked at random was paid with a credit card or a debit/ATM card. So we're looking for this probability, and all I'm going to be doing is looking at the table here, and I can see that, I have 25 and 15 cards out of the 100, or I can say 0.25 and 0.15 and add those together, are going to be in this sample space. So approximately 0.4 or 40% of them do. For B, what's the probability that the transaction being picked for us to look at is paid with cash or some other method other than a check, a credit card, or a debit ATM card. So we have cash, or we have the other category, and I can see those probabilities are 0.14 and 0.09, and that totals 0.25. So the probability, or the percentage of that we expect out of this group would be about 25%. So this is the beginning of this. If you have any further questions, please make sure to ask about them in class. I'll see you then. Have a good day.